Alright, today we're going to talk about section 7.3, estimating a population mean with sigma known. Alright, I think we'll find a lot of the framework for 7.3 has already been laid in section 7.2. Remember, well, before we tackle it in earnest, the population mean is mu for any population, and remember sigma is your population SD. And let me erase that. It's your population standard deviation. Alright, so we're going to be estimating mu, assuming that sigma, your population SD, is known in section 7.3. Alright, before we go on, let's talk about section 7.2. Take a look back. Recall in 7.2, we talked about population proportions with some characteristic. If we've got some huge population, and we're talking about some characteristic of interest, be it left-handedness, high blood pressure, any characteristic of interest, if I had some population X, where X represented all the numerical measurements of this population, P, little p, was our population proportion with some characteristic of interest. Alright? Little p, recall little p, we never really know for sure because populations are so huge. So what we did in section 7.2, we created an interval estimate for P, or what we called a confidence interval, in this fashion. Now we did this two ways. We showed you how to use the calculator operator, one prop z int, to construct this confidence interval, and we also showed you how to do it by hand. In any case, we got upper and lower bounds for our confidence interval estimate for little p. And we're going to be doing something very similar in section 7.3 today. In section 7.3, we're going to be estimating not a population proportion, but a population mean. Remember, the symbol for population mean is mu, and we're making this condition, which we'll talk more about when we tackle 7.4, that the population standard deviation is known. And we'll look at that in a couple of examples. All right? So graphically, I've got a huge population with perhaps millions of numerical measurements. One might ask the question, what is the population mean of those measurements? Well, that symbol we use to represent population mean is mu. And of course, we never really know mu for sure because there's so many elements in this population. Alright, so the book talks about two different estimates for mu. One is called a point estimate. Well, if I ask you for a point estimate for mu, you might tell me, well, let's just grab a sample and compute the mean of that sample. And perhaps that sample mean is a good estimator of the population mean. So if we take a sample, every sample can have a mean computed. Well, the idea here is maybe point estimates are a good estimate of mu. Maybe x bar is not a good estimate of mu. So the idea is perhaps there is a better way. Let me label this. X bar is our sample mean. Alright, so better way perhaps. And much like we did in section 7.2, will create a confidence interval estimate not for P as in 7.2, but for mu. That is our goal today. Right. It'll be constructed in much the same way. Well, we'll have a high boundary and a low boundary for my confidence interval estimate for mu. I'm going to center this around a sample mean. Alright, to create an upper and lower bound for that interval estimate, I'm going to successively add and subtract a value cap E, which is, of course, our margin of error. Now, the formula for E changes here a little bit in section 7.3. We'll talk about that in a minute. This is my confidence interval estimate, and the idea here is perhaps mu will land in this interval. Maybe mu is not in this interval. The idea is we'll never know for sure. What I can say is with a certain level of confidence, similarly constructed intervals will actually contain mu, at least with a certain level of probability. Alright, so things hopefully look much the same as in 7.2. Let me delete this and get a fresh layer. And let's delve right in and show you how to create these confidence interval estimates. One thing I want to highlight before we show you how to construct the confidence interval is give you our formula for E. Again, I want to show you the formula for E because just like the formula for E in 7.2, it involves the calculation of a z-score. Right, and that will remind us which operator to use on our calculator here. Right, so this formula, z sub alpha over 2 times population SD divided by the square root of n, is similar to the formula that we saw in section 7.2. Yes, similar to the formula we saw in 7.2. The good news is, well, I can show you how to grind this out by hand, but there's another operator on the calculator that will construct these confidence intervals for us. Let me write this down. But the TI 83 or 84, of course, will compute E for us internally and the confidence interval, which of course is our ultimate goal. Alright, let me show you how to compute the confidence intervals with the calculator, and let's take a little bird's eye view of this new operator. To estimate mu with sigma known, again we're making that agreement that sigma is known, we're going to use an operator on our calculator called the z-interval command. Alright, let's take a look at what this command looks like. If you go to your calculator, hit your Stat button, highlight and select your Tests sub-option, and then scroll down until you see this command, highlight it and select it to call it up into your home screen. Z-interval is the name of this command. Now remember, if you're approximating mu, estimating mu, remember this calculation ultimately depends on a z value that's computed upstream. Right? We point that out to make it a little easier to remember. You're going to use the z-interval operator. Alright. Basically, the z-interval operator on your calculator looks something like this. It offers you two different input modes, either raw data or summary statistics. It prompts you then for a sigma value, a sample mean value, an n value, a confidence level, and of course there's once you fill in all these items, there's a calculate item to highlight and select. Alright, we're going to start out in the summary statistics mode, and let's cite to you an example of how to use this z-interval command. I will look at example 1. It's on page 347. And let me turn there and read through the example. Example 1. Weights of men. People have died in boat and aircraft accidents because an obsolete estimate of the mean weight of men was used. In recent decades, the mean weight of men has increased considerably, so we need to update our estimate of that mean so that boats, aircraft, etc. do not become dangerously overloaded. Using the weights of men from data set 1 in Appendix B, we obtain these sample statistics for the simple random sample. Alright, so our goal here is to estimate the population mean of adult men, and we've got this sample data. N equals 40. Our sample mean is 172.55 in pounds. Alright, and this last sentence in the problem statement says research from several other sources suggests that the population of weights of men has a standard deviation given by sigma equals 2.6. So you'll see that language a lot. I'll say previous studies or research from other studies gives us the sigma value of whatever. In this problem it's 26. Alright, so what do we want to do? If I turn over leaf, it has an A, B, and C section. A, find the best point estimate. Find the best point estimate of the mean weight of the population of all men. So my point estimate of mu, well, I suppose the best point estimate we can imagine for a population mean is a sample mean. And the sample mean for this problem was 172.55 given to us. Alright, so this I'm calling my point estimate of mu. In other words, the sample mean is my point estimate of the population mean. And again, maybe that's a good estimate, maybe that's not a good estimate, depends on the sample, I suppose. Alright, perhaps B has a better way. B says construct a 95% confidence interval estimate of the mean weight of all men. Alright, so I'll summarize it like that. We want a 95% confidence interval for the population mean weight of all men. Well, there's millions, billions of men to measure, so we can't get an exact value, but what I'm going to do, again, is create a confidence interval estimate, right? Alright, let's see. Let me write down this information in this problem again. We had a sample size of 40. We had a sample mean of 172.55. The population SD was given to us as 26 in pounds. Alright, so we're going to use this Z interval command on our calculator. So press the stat button, select and highlight and select the tests sub option, scroll down and select the Z interval option. Alright, the calculator then prompts me for an input mode. Data we're going to do later. We are given summary statistics here, so choose the statistics input mode, highlight and select. You are then prompted for a population SD, which is 26. Go ahead and enter that in. Your sample mean is 172.55. You're then prompted for an n value, which of course is 40. And your C level, which the calculator prompts you for here, we're going to put in 0.95. Alright, so highlight calculate and select, and you get the following result: 164.49, comma 180.61. Again, the calculator output is in interval notation. Both the author and I prefer this, what we call the double-sided inequality notation. I'll write it like this: my 95% confidence interval for mu, not p, mu, the population mean weight of all adult men, looks something like this. Well, we got a lower bound of 164.49. We got an upper bound of 180.61, with hopefully mu trapped somewhere in between. This is my 95% confidence interval for mu. Alright, and again, much like in section 7.2, I can claim that 95% of similarly constructed intervals actually contain mu. Okay, again, based on techniques of probability and statistical inference. Alright. Let's go on to another example. This is number 21 from the homework list on page 353. You turn there. Number 21. Let's read the problem. This is a very similar problem. Weights of women this time. Using the simple random sample of weights of women from data set 1 in Appendix B, we obtain these sample statistics. Alright, let me write them down as I read them. The sample size, little n equals 40. The sample mean weight, remember we're talking about women here, is 146.22 in pounds. And it states research from other sources suggests that the population of weights of women has a standard deviation given by sigma equals 30.86. Okay? Alright, they give us a part A and B. Very similar to the last example. Find the best point estimate for the population mean weight of all women. So I'll shorthand it like this: my point estimate for mu, where mu is the population mean weight of all adult women, is nothing more than the sample mean weight. So in this problem it's 146.22. Notice this value might change depending on what sample you pick. Some samples are better than others, or more representative than others, I suppose. Alright. Part B asks us for an interval estimate, not a point estimate, an interval estimate. Find a 95% confidence interval estimate for the mean weight, population mean weight of all adult women. Okay? Alright. Again, we'll use our Z interval command on our calculator. Let me write that down. Use Z interval. And this is the second of several commands we're going to be using in that tests submenu under the stat button operator. So beware of that. There's more coming. So we'll press stat, tests, scroll down to Z interval, highlight and select, again, for the input mode, highlight and select stats. If you're given summary statistics and not given raw data, you'll want to use the stats mode. It prompts me for sigma. Remember, sigma was given to us as 30.86. The sample mean was 146.22. Sample size is 40. And the confidence level, of course, 0.95. Alright, go ahead and highlight and select calculate, and we get the following result: 136.66. I need some more room here. Now the calculator returns 136.66 and 155.78. So these are my boundaries for my confidence interval. I prefer we write it like this. Now remember, we're estimating mu, not p here. P was in section 7.2. Mu is in section 7.3. 155.78. This is my 95% confidence interval for mu, where mu is the population mean weight of all adult women. Okay? All right, I want to talk about the data input mode, give you an example of how to use that mode. Let me get a fresh screen here. Oops. What the heck happened? All right, let's try number 27 on page 353. And let me read the problem out. Blood pressure levels. When 14 different second-year medical students at Bellevue Hospital measure the blood pressure of the same person, they obtain the results listed below. Assuming that the population SD is known to be 10, construct a 95% confidence interval estimate of the population mean. Alright, so what do they tell us here? They tell us we've got a sample size of 14 blood pressure measurements. We are told that the population SD for all these blood pressure measurements is known to be 10 in millimeters of mercury. We want our level of confidence to be 0.95. Right? So we want to construct the confidence interval here. Well, what they don't tell us is the sample mean. Well, they give us raw data instead. Well, what I can do is compute the sample mean from these 14 values by hand, or I can use the data input mode with this z interval command. So that's what I'm going to suggest here. Use data input for the z interval command. Alright, how do we do that? Well, the first thing you got to do is put your raw data into list L1. Let's get an overview of what the data input looks like, the data input mode looks like before we actually put the data in. Let's take a look. Press on your calculator stat, then tests, then of course z interval. Alright, the first thing the calculator prompts you for is your input mode, and I would like us to highlight and select data because we're going to be inputting raw data here, right, as stated in the problem. Alright, notice the screen changes a little bit. Still, they prompt you for sigma. but instead of a sample mean, they ask you for a list. Now the default hopefully is list L1. So what this is the list address where you enter your raw data. Let me write this down. This is where the raw data is entered, and L1 should be fine. It then says a frequency selection, just leave it at 1. Hopefully the default is 1. And then, of course, they'll prompt us for a confidence level and then a calculate operator when all these things are entered. Okay? Alright, so the first thing we should do really is enter our raw data into list L1 and then call up the z-interval command. To enter the raw data into list L1, we haven't done it in a while, maybe we should refresh our memories. We hit stat, edit, and hopefully this comes to remembrance now. You clear the old data from L1 and enter the new data into L1, as we've done many times before in the course. Alright, once you've entered in the new data, now, again, to construct the confidence interval, hit stat, tests. Again, we're calling up that z-interval command. Input mode, we'll want data. For this particular problem, recall the standard deviation was given to us as 10. The list default hopefully is L1. The frequency, leave it at 1. Hopefully the default is 1. And the confidence level is 0.95. Alright, so we can work this z-interval command entering in raw data just as well as we can with summary statistics. Alright, so the output of the calculator, once I highlight, calculate, and select, I get 128.69 on the low end and 139.17 on the high end. This is my 95% confidence interval for mu, where mu is the population mean of adult women or women's weights. Okay? Alright, so we did 3 examples of using the z-interval command to estimate mu, where sigma is known. Okay, we'll talk more about that concept of sigma being known in the next class when we talk about section 7.4. Just as a teaser, in 7.4 we'll still be estimating mu, but we are going to assume sigma is unknown. And as we'll see, that's a much more realistic scenario. Alright, we're reaching the 29-minute point, so we'll call it a day. This concludes section 7.3, estimates of population means with sigma known.